for the introduction and the invitation, and for organizing this nice seminar series, in particular for choosing this exquisite mascot for the large charge program. So I'll be talking about this paper that came out last month, and which was done in collaboration with my excellent collaborators, Umang Mehta and Gabrielle Cuomo. Umang is a PhD student at the University of Chicago, and Gabrielle recently joined Stony Brook as a postdoc. So the nice thing about talking to a large charge audience is that I basically don't need to give an introduction, but let me still say a few words of kind of motivation and context. So we'd like to understand quantum field theories, and perhaps more specifically conformal field theories, away from the lamppost of weak coupling. And one of the kind of basic questions one can ask about a conformal field theory is, how does it respond to probes, to external probes? So in general, there are many probes one could consider, but there are some that are universally present in any CFT, for example, temperature, or if you have a global symmetry, chemical potential. And these potentials in the thermodynamic limit in general will probe heavy operators in your CFT. So those who know me know that I like temperature, but I also like chemical potential. And today's talk will be about this. So a finite chemical potential at 0 temperature probes special heavy operators, which are the lightest at a fixed large charge. And the kind of most basic question you can ask about your CFT in this context is, what phase, if any, does it enter when coupled to finite chemical potential? So in the thermodynamic limit, chemical potential is the only parameter in the game. So any chemical potential is equivalent as long as it's not 0. So there's a number of possibilities, but not that many, maybe because of lack of imagination. One option is that the CFT becomes a Fermi liquid with a finite chemical potential. This happens if you start, for example, with free fermions. Another possibility is that it becomes a superfluid. And people here know that by now a number of CFTs have been shown to indeed enter a superfluid phase. And this is thought to be a pretty generic possibility, perhaps more generic than the Fermi liquid. But there are also more exotic possibilities. It could become an extremal black hole, although it's unclear if these states are stable in any CFT with a finite number of degrees of freedom. And it could also become, for example, a non-Fermi liquid, whose definition is basically none of the above, which is why there aren't that many options. So I think it would be really interesting to explore what phases are actually realized in CFTs, which ones are there more possibilities, which ones occur. I won't be doing this today. What I'll be doing is that I'll consider CFTs that enter a superfluid phase at finite chemical potential and explore the consequences. So I'm basically following the lead of this paper. So here I was talking canonically in terms of the chemical potential. Microcanonically, what this assumption means is that large charge operators create a superfluid state. And this rather mild and pretty reasonable assumption has a large number of consequences. It leads to very sharp predictions on many things. For example, not only does it fix this curve, this leading trajectory of the lightest operator, it also tells you what the spectrum of low-lying operators right above this edge of the spectrum is. It's comprised of these superfluid phonons. And one can also use this, the superfluid effective field theory you get to compute correlation functions, and for example, OP coefficients involving these heavy operators. So just to stress really the power of this approach, what's really striking is that it's going to lead to a number of predictions of CFT data in terms of a small number of Wilsonian coefficients of the effective field theory. In fact, to leading order, it's really just the CFT data is just going to depend on the leading Wilsonian coefficient, the superfluid stiffness that I'll call C1, which in particular appears in this slope of the leading trajectory. So you could take this as a definition of C1 if you want from the perspective of the CFT, but the same C1 is going to control a number of other things. For example, it's determining the leading interactions in the effective field theory. So as such, it's going to control the leading deviations of the spectrum from the free phonon, free Fock space spectrum. For the same reason, the C1 is also going to control thermalization of the superfluid. As you go away from the edge of the spectrum, it's going to determine what type of hydrodynamics emerges as you go away from the edge. And as I mentioned before, the same coefficient also controls OP coefficients between heavy operators and light ones. So here I showed two examples where the light operator is either the U1 current or the stress tensor, and the heavy operators are the kind of superfluid ground state, and then the ground state plus a single photon with spin j. So here I'm computing some OP coefficient involving these red states. And you can compute these OP coefficients, and they have universal expressions that only depend on the quantum numbers of the operators in the game and the same C1 coefficient to leading order at large charge. So there's really a lot of power to this statement that the large charge sector is described by a superfluid. And here I should say that I'm specializing to 3 dimensions. So previous work on the large charge expansion has focused on CFTs that have parity as a symmetry. Today, I'll tell you about what happens, what's new for CFTs that don't have parity in 3 dimensions. So before I go into the meat of the talk, let me give you 4 of our key results that I want you to take away from this talk. The first is that for parity violating CFTs, there's a single one derivative correction to the effective field theory, which is interesting because the leading correction in the parity preserving case is 2 derivatives. So this is coming before, it's more important. And although it's a correction, as the leading parity violating effect, it's going to give the leading contribution to parity violating or parity odd CFT data, such as OP coefficients. And so I'll explain how this happens. This new term is also a little bit funny. It's kind of like a Wessumino term. And this leads to a number of striking consequences. One is that its coefficient has to be quantized. I'll call its coefficient kappa. And another related one is that if we place the effective field theory on the sphere, this term forces the superfluid ground states to have kappa vortices on the sphere. So this has a number of consequences. It means that these large charge states in parity violating CFTs will look a little funny. They're going to have, these vortices are, for example, going to lead to corrections to the dimensions of these large charge states, but they're also going to lead to a whole spectrum of vortex excitations that I'll talk about, and that happen to be very soft. So they're even lighter than the photon excitations. Finally, all of these, yes, question?
I'm sorry, I didn't, if you were to put the theory on a different kind of spatial slice, would the number of vortices always be proportional to the Euler number of the slice, or is it not that simple? Okay.
Yes, it would be kappa times the Euler number.
Okay, thanks.
Yeah. Okay, and so all of these predictions from the EFT, in principle, they could apply. There's no assumption of weak coupling. They could apply to both weakly and strongly coupled CFTs, but it would be nice to see it happen. So I'll show you an example of a weakly coupled parity violating CFT that I'll call ANYON CFT, where all of this happens. So it's basically a Chern-Simons matter theory that's very weakly coupled. Okay, are there any questions here before I go into the meat of the talk? All right, so this will be the plan. As a warm-up, we'll start by considering this effective field theory on the plane. So I'll show you what the effective field theory looks like, what this new term is, and how it controls parity odd data of the CFT. And then we'll look at this special weakly coupled CFT, ANYON CFT, and I'll show you that it becomes indeed a superfluid at finite density. But of course, to study the large charge spectrum, we're instructed by the operator state correspondence to put the EFT on the sphere if we want to study heavy large charge operators. However, of course, at very large charge, at fixed charge density, the sphere looks a lot like a plane. So the plane is more than just a warm-up. It's also going to capture the very leading large charge behavior. But by placing the EFT on the sphere, we'll be able to make much more precise predictions on what happens. And we'll see some surprises, in particular the fact that the ground state has vortices. I'll explain how to quantize these vortices. And then I'm going to revisit this ANYON CFT and see how these predictions work in that situation. Okay, so let me start on the plane, and let me start by briefly reviewing the parity preserving case, which you guys probably know. So the ingredients there are the symmetry breaking pattern, in particular the fact that the U1 symmetry is spontaneously broken, along with some space-time symmetries, and the fact that we're studying it at finite density or finite chemical potential. And once you have this input, there's an algorithm, the cosec construction, which will spit out the most general effective action in a gradient expansion that's consistent with symmetries and with a degree of freedom nonlinearly realizing the spontaneously broken symmetries. And this degree of freedom is the superfluid photon, or the Goldstone phi. So this is what the leading EFT looks like, and then there's going to be subleading corrections. Notice that these subleading corrections have 2 extra derivatives in addition compared to the leading term. And so this effective field theory is a derivative expansion where the higher derivative terms are going to be suppressed by the charge density, which plays the role of the cutoff. And ultimately, when we compute CFT data, they would lead to 1/q suppressed corrections to observables. So to study parity-violating effects, it's going to be useful to dualize the theory. So to replace the scalar with a gauge field, in 3 dimensions, a photon has a single polarization, so it has the same number of degrees of freedom as a scalar, and we can work in either with either variables. And while doing this, it's also going to be useful to keep track of what's happening to the currents as we do this. So the superfluid has 2 internal symmetries. It has a U1 symmetry, which is the microscopic symmetry that the CFT had, which definitely has to be there in the effective field theory. And it also has an emergent one-form symmetry, which counts the winding of the superfluid phase. Okay, if I turn on a winding in my superfluid, it's not going to decay; it's going to be conserved. This is also the reason why superconductors superconduct. Okay, you don't need the supercurrent won't decay. Notice that this higher form current is identically conserved. The divergence is just 0, whereas this current is only conserved on shell. When we dualize, this gets flipped. Which current is conserved on shell gets flipped, and the regular current, the U1 current, is just is identically conserved and is counting basically the monopole number, whereas the higher form current looks like this. The regular symmetry acts like a shift symmetry on the scalar degree of freedom, whereas the higher form symmetry acts like a shift symmetry on the photon. So if we dualize and write the action in terms of these variables, what this leading d phi cube term becomes is this f to the 3/2. Okay, and one could similarly look for one could similarly dualize it and look for these 2 derivative corrections. But I'm not going to do that because there's already a new 1 derivative correction that one can write down if parity is not a symmetry, and it looks like this. So let me spell it out a little bit, and I should say it was first introduced in this paper. So here there's 3 letters that denote the same thing: A, F, and U. So A is the photon, it's the gauge field, A mu. F is, as usual, the field strength, dA, and U is a unit vector built out of F. Okay, so U is basically the superfluid velocity. But these are all the same degree of freedom. It's just that it's a little more convenient to write this term in this way. Okay, so let's look at, and it's a 1 derivative term because there's a bare A, and so if you put one of the derivatives on A, it would just have 1 derivative compared to this leading term. So let's look at it a little more closely. I can write it in this way as A mu contracted with an object that I'll call the Euler current, or that they call the Euler current, and which has this form. So at face value, it looks like it's not gauge invariant, but under a gauge transformations, after integration by parts, it is gauge invariant because this current is identically conserved. If I take d mu of this, I'll find that so U is a unit vector, so du has to be orthogonal to U, and this will be a triple product of 3 vectors that are all orthogonal to U, so it has to vanish identically. Okay, so that's why this term is gauge invariant after integration by parts. Here, we also see why it was important to dualize, okay, because there's a bare A appearing here. In particular, this term is explicitly breaking this higher form symmetry that I mentioned earlier. Whereas in the phi language, it's hard to imagine how to break this symmetry explicitly since it's identically conserved. On the other hand, this higher form symmetry is an emergent symmetry, so we do expect it to be broken by irrelevant terms in general. Or another way of saying this is that if I wrote this back in the phi language, it would look non-local. But in this language, it's clear that it's an allowed local term in the effective field theory. But it's a little funny. It has this bare A, and that leads to some consequences. In particular, imposing invariance of the action under large gauge transformation, where the transformation wraps by 2 pi around some cycle, forces quantization of this kappa. So one can show, I'll show you some examples in a little bit, that if you do this, so the integral of A will give you 2 pi, and then the integral of the Euler current on a 2-dimensional manifold gives the Euler characteristic of that manifold. I'll show some examples in a bit. And so this implies that for invariance of the action up to 2 pi I, you need kappa to be integer quantized. So this kappa is basically an integer that characterizes parity-violating CFTs at large charge. And it's kind of similar to C1 in the sense that it's not really, part of the CFT data that can be probed with light operators only. It doesn't appear in the algebra of light operators. It's really something, it's a property of the CFT that you can only see by looking at these heavy or large charge operators. Okay, so what does this kappa do? What is it? What physics is it related to? Well, in the context of superfluids, it's been associated with a transport phenomenon called the Hall viscosity. So viscosities in general tell you about how your system responds to strain, to small strains. And the Hall viscosity is a parity-violating response to strain. And one way to picture what it does is if you take your superfluid and you squeeze it, because of this term, it's going to start rotating. So this is clearly a parity-violating effect. So response to infinitesimal, linear response, infinitesimal probes can be studied by 2-point functions in the finite density state, and this is the formula that basically defines this Hall viscosity. So it was originally considered in the context of quantum Hall systems, but there's been some interest in Hall viscosities in superfluids as well a little more recently. So we can compute this Hall viscosity in our superfluid. We just write down the expression for the stress tensor. It receives a contribution from this kappa term in the action. This is the ideal stress tensor. This is what the contribution looks like. And now if we expand around this finite density solution and plug this in here and just use our propagator for the Goldstone, this is what you would find. You would find that the Hall viscosity is given by kappa, this kappa term divided by 4, up to the background density, which sets the scale. So transports in CFTs can be probed by 4-point functions involving these heavy operators. And at an even more basic level, we could imagine inserting a complete basis of states in the middle, so that we expect off-diagonal OP, heavy light OP coefficients to be sensitive to these transport phenomena. So this should be true even away from the edge of the spectrum. If our system has a Hall viscosity, these odd OP coefficients are going to measure this Hall viscosity. But in the middle of the spectrum is exponentially dense. There are many of these states. And so one usually can only make average statements. But on the edge of the spectrum is very simple. And we know precisely which states inserted in the middle are going to give the dominant contribution and reproduce, saturate this Hall viscosity. And it's single phonon states. Okay, so Q prime is going to be a single phonon state. And the reason is that the stress tensor is creating, if you expand it, it's going to create a single phonon state plus higher phonon states. But because our theory is weakly coupled, the single phonon state is going to give the dominant contribution. Okay, so we can compute these OP coefficients following, so we're basically computing OP coefficients involving 2 heavy states and the stress tensor or the current. So one can do this following these papers. The idea is to expand, as I said, around the finite density solution in terms of superfluid excitations. So you expand the stress tensor. It has an expectation value part, which won't appear in these off-diagonal OP coefficients. Then it has a leading term coming from C1. And then it has a parity-violating piece coming from kappa that looks like this. So to compute this OP coefficient, we just plug this in here. Here, Q bar is the ground state, and Q is the ground state plus a single phonon with momentum J. Okay, and then just with the algebra of these raising and lowering operators, you can compute these OP coefficients. So I had shown this one before, that there's a parity even. There's a single parity even and a single parity odd OP coefficient. The parity even one only involves the quantum numbers of the operators and this C1 coefficient that we could already measure from this leading trajectory. Whereas the parity odd one, as expected, involves these things, but is proportional to kappa. So it's a way, you could say, to measure kappa in the CFT data. Okay, So in a little bit, I'll explain how to put this effective field theory on the sphere and see, and we'll see that there's a lot of interesting surprises there. Before that, I just want to take a step back and think about which CFTs these predictions would apply to. So of course, they could apply to both strongly coupled and weakly coupled CFTs, but it would be nice to actually check that it happens in a weakly coupled setting. So there's been a number of checks for parity preserving CFTs. There's a number of weakly coupled CFTs in particular that are known to enter superfluid phases at finite density. At strong coupling, of course, it's harder to check things analytically, but there's very interesting numerics that looked at the Wilson-Fisher CFT in 3 dimensions, and didn't quite show that it enters a superfluid phase, but it showed that it has this relation of the scaling of the lightest operator at large charge, which is already a good hint. So here I'm going to add a parity-violating CFT to this list of examples where we know that the CFT enters a superfluid phase. Okay, so there's a number of candidates that are candidate CFTs that are parity violating in 3 dimensions. There's a whole zoo of Chern-Simons matter theories. I'm going to focus here first on 2 families of them. So where I have a SUN or UN gauge field with some Chern-Simons level coupled to a single flavor of fermion. And in both of these families of CFTs, there's a U1 symmetry carried by a current, which is either the fermion number current in this case, or the kind of monopole number current in this case. So these theories have been studied a lot at n equals infinity, where there's an interesting double scaling limit. And it seems that they're not superfluids at finite chemical potential. In fact, it's been shown that they have the properties of a Fermi liquid. But it's well known that Fermi liquids have an instability towards superfluidity. And so you could ask if these results are robust against 1/n corrections. I think they probably aren't. So you could ask, does one ever obtain a superfluid for finite n? So I will show that this does happen for a very special case when n is 1 and when the level of the Chern-Simons term goes to infinity, so that the theory becomes weakly coupled. So the theory that we're looking at is the following. We have a single fermion, a single Dirac fermion, which is coupled through a covariant derivative to a fluctuating gauge field with a Chern-Simons term at level k. And so when k goes to infinity, if you canonically normalize the gauge field, you'll see that the coupling is going to 0. So it's going to become weakly coupled. So to leading order in k, it's really just a kind of decoupled fermion and a decoupled gauge field, except for a constraint. The A0 equation of motion is a constraint equation, analog of a Gauss law, which fixes the fermion density to be equal to k times the density, the actual density, or the actual density. So in other words, the number of the fermion density is going to be k times the magnetic field in the system. But apart from that, to leading order, things are basically free. But what this means is that if we study the theory at finite density now for applications to the large charge, to study large charge operators, what we're going to have is a bunch of fermions in a magnetic field. So a finite density of fermions in a magnetic field with the density equal to k times the magnetic field. So the fermions are going to fill k Landau levels. They're exactly going to fill k Landau levels, which means that the fermion sector will be gapped. Okay, the gap to the next Landau level will be non-zero because the last Landau level is filled. So what we can do is integrate them out and obtain an effective field theory for this gauge field. So you can do that. And to leading order, what it does, what integrating these fermions out is that it produces a Chern-Simons term, which exactly cancels the Chern-Simons term we had in the original action. One way to see this is that the response of k Landau levels to an electric field is the following. It has this Hall connectivity, sigma xy equal to k. This is just the integer quantum Hall effect. And so because of this response, it's going to lead to this term in the effective action, which will cancel the leading Chern-Simons term. But it is also going to generate higher derivative terms. Okay, it is going to, integrating out the fermions is going to generate Maxwell-like terms. And in fact, if you do this, you'll find the following next order contribution which has this form, which is exactly what you would get for a conformal superfluid, in particular the speed of sound. So we're left with a gapless photon, which is like a superfluid phase in 3 dimensions. And it has the right speed of sound, 1 over square root of 2. So this is what you would get if you expanded the dual action that I showed earlier. In particular, we can even read off the coefficient C1, this leading coefficient in the large charge program that controls all of this data in terms of this coefficient over here. Okay, and so now that we have this coefficient in hand, we can look at the dimension of the lightest operator, the fixed large charge, in this formula, and this is what one gets. So there's a simple expression for the dimension. So the claim is that this theory of ANYON superfluids or of ANYON CFTs has a spectrum of large charge monopole operators that have this dimension.
Luca,
yes.
Just to make sure, this is a double scaling, right? Where you send k to infinity, q to infinity, and you keep the.
So here it's a bit simpler because I'm on the plane. So I'm really q equals infinity from the start.
Okay.
I'm on the plane, so q is equal to infinity. It's rho times the volume, which is infinity. So k is much smaller than q. Q is the biggest number.
Okay.
Yeah. I'll talk a bit about double scaling limits when we go on the sphere.
Thank you.
Yeah, here it's q to infinity first. In fact, in these papers, it was an opposite limit. So it's not quite correct that it should agree, but it does agree. And I'll explain why, maybe. This expression was found previously in a slightly different limit. But here we find much more than just prediction for the for the dimension of this large charge state. We're saying that it creates a superfluid state. So that comes with a whole baggage of the superfluids. So not only does it have this dimension, but also it comes with its tower of phonon friends, low-lying spectrum, and so on, and correlation functions that we can compute. Okay, so I'll revisit this in a bit when we after discussing how to go on the sphere, which I'll do now. So are there any questions so far before I move on to the sphere? Okay, if not, let's do it. All right, so let's now place the theory on the sphere as a way to study the large charge spectrum. By Weyl invariance, if you know the effective field theory on any manifold, you know on any other manifold, as long as you write it in a Weyl invariant way, and this is the way to write it. This is the way to do so. So the leading term simply looks like this, and the kappa term has this form. It still looks like a mu contracted with the Euler current, except the Euler current now looks like this. So the derivatives are replaced with covariant derivatives, and it has this Riemann tensor term. So it's easy to check that this is the expression you need for it to be covariantly conserved, identically conserved. And this was already done in this paper. All right, so as I said before, this term is breaking the higher form symmetry that shifts that shifts mu. In fact, it's the only term in the leading order action that does this. Even the C2, the other coefficients we had in the parity preserving case that are in these dots, they don't break this higher form symmetry. So this is the only term, at least to this order, that does this. And that has some consequences. It means that if I computed the divergence of my higher form current, I wouldn't find 0, but instead I would just find this Euler current. Okay. But there's a problem with this equation. So let's look at the nu equals 0 component of this equation. And let's integrate it over space, over some spatial manifold. So as I said before, if you integrate this Euler current over a spatial manifold, this gives you the Euler characteristic. I'll give you an example on the sphere in a bit. So on the right-hand side, we'll have kappa times the Euler characteristic. But on the left-hand side, this is an antisymmetric, it's a higher form current, it's antisymmetric. So if nu equals 0, mu is a spatial index. And so it's just a total derivative that I'm integrating over the sphere. So it's going to give me 0. Okay, so I land on this equation, which is no good. And what's happening is that this Euler term is, remember, this higher form current is the winding of the superfluid. So this Euler term is sourcing vorticity in our superfluid. And the only way we'll be able to accommodate for this is if we actually have vortices. Okay. So I'll explain this in dual language because it's even easier to understand in dual language, I think. So let's work in dual language, and let's focus on the sphere and expand around finite density. So my current will take this form. It's approximately going to be given by a constant charge density, and it's going to point in the time direction. So to really leading order in the background, the Euler current will also point in the time direction. If you put in this expression, the derivatives will just give you 0, and you'll be left with this this Riemann term, which picks up the curvature of the sphere. So it's going to be equal to this expression, 1 over r squared. R is the radius of the sphere. Notice that if I integrate this over the sphere, it's going to give me 1, which is exactly the Euler characteristic of the sphere divided by 2. Okay, so on the right-hand side of our non-conservation equation, we have this. Let's focus again on nu equals 0, and now I'm writing it in terms of my dual variables. Basically, this higher form, the nu equals 0 component of this equation is Gauss's law in terms of the dual variables. And I'm dropping some factors, but this is basically what it looks like. So we're on the sphere, and what we're seeing is that this Euler current is sourcing a finite density on the sphere. But that's no good. Gauss's law has to hold on the sphere, otherwise the electric field will have nowhere to go. So what this means is that we're going to have to introduce charges to neutralize the total charge on the sphere. Okay, and the amount of charges that we're going to have to introduce will depend on kappa. Okay, so we have to introduce these degrees of freedom in our effective field theory. So how do we do this? Well, to leading order, charged matter will couple to the gauge field through Wilson lines. So if I have a bunch of charged particles or vortices in the Goldstone language, they're going to couple in this way to my gauge field. So XP are the world lines of these charged particles, and P runs from 1 to the total number of particles or vortices that I have. So now that I introduced this term in the action, and there's going to be higher derivative terms, but this is the only, this is the kind of leading coupling that I'll need for today. So now we see that there's a new term where A is appearing, there's a bare A appearing. So it's also going to give a contribution to the right-hand side of this equation. And in fact, this non-conservation equation is now going to look like this. Gauss's law is going to look like this. So if I integrate it over all of space, here I have a delta function located at the position of all of these particles. So if I integrate over my sphere, I'll find that Gauss's law holds. This is 0, as long as I have exactly kappa charges or kappa vortices. Okay, so what we have in the ground states and the low-lying states of our superfluid is a system with kappa charged particles interacting with a photon. So in particular, they're going to interact through a Coulomb force because of this photon. Good. So let me make a comment here. So vortices have appeared in the large charge context in this nice paper by Gabriel and collaborators, where they were asking a different question. So this was for parity preserving CFTs, and they were looking for the lightest operator at large charge and a fixed spin. So for small spin, the operator that's the lightest is just a superfluid phonon on top of the ground state. But for large enough spin, it becomes more advantageous and energetically to build a vortex-anti-vortex pair. Okay, and so these vortices, one can show that they have some angular momentum. This is just coming from the fact that the superfluid is flowing around the vortex. So it has some classical angular momentum that you can compute. It's equal to Q over 2. So it's pretty large. But if the vortex-anti-vortex are very close to each other, their angular momenta will almost cancel. And so the total angular momentum won't necessarily be too large. But as I increase the angle between the vortex-anti-vortex, it's going to increase until it finally reaches its maximum value, which will be Q, when the vortex and anti-vortex are on opposite poles. Right. So here it's a little different. Here we didn't try to turn on spin. The vortices are here whether we like it or not. In fact, we found that all states have to have a non-vanishing vorticity. In particular, we'll have a net number of vortices. So say 4 vortices and no anti-vortex. Okay, so let's try to figure out what configuration the vortices will be in the ground states. So as I said, they're going to interact through a Coulomb interaction. Yes.
Okay. Can I disturb you again?
Yes.
Do you have an idea of what these things with vortices would correspond in terms of the other variables, so the phi's? I mean,
yes.
Before you dualize to the Luca theory.
Yeah. Well, it's phi is literally winding around the vortex. So if you're far enough from the vortex score where you trust your EFT, you can measure phi. You know, let's say you measure phi, you'll really see it wind by 2 pi around the vortex. But in the vortex score, there's new degrees of freedom. You know, you would say the symmetry is restored, and there's some new stuff that's not just phi in it.
Okay.
And that we're modeling as a point particle.
Okay.
But yeah, it's gonna have, it might have some structure. So there are, you know, there are these vortices will be things from the original theory, which might have some structure, spin, and so on. That will appear here in kind of corrections. But to leading order, they're going to couple like point particles. Okay, so let's try to figure out what their configuration is in the ground states. So as I said, these vortices are interacting with each other through the Coulomb interaction because of the photon. We have a massless photon. And in 2 dimensions, this is what in 2 + 1 dimension, this is what the Coulomb interaction looks like. It's a log potential. So we have a classical minimization problem, which actually is non-trivial. It goes under the name of White's problem. And the solution isn't known in general. The configuration of vortices that minimizes this you know, rather simple function isn't known in general. Some special cases are known. Some of which were, you know, only found not even so long ago. And so let me give you a few examples. The small numbers of kappa are pretty obvious. So if kappa is equal to 1, I have a single charge. I can just put it wherever I want. It doesn't matter. When kappa is 2, I just put the 2 charges on opposite poles. When it's 3, they're going to be at the corners of the equilateral triangle. And when it's 4, they're going to be at the corners of a tetrahedron. So for general kappa, this configuration isn't known, but there's a very useful fact about this configuration, which is known, which is that one can show in general that the center of mass of this configuration is always at the origin, except of course for kappa equal to 1, where you have a single vortex. What this means for us is that this total angular momentum is always going to cancel, exactly going to cancel, because they're always, you know, the sum over xp is just going to give us 0. They're always going to point in opposite directions. So the ground state, at least what we find at the classical level, is that this lightest large charge state will have 0 spin, except for kappa equals 1, which seems like a weird special case.
So
one thing I didn't, yes, question?
Oh, sorry, this is a dumb question, but you wrote that distance inside the log in like vector notation.
Yeah.
Does that distance mean the geodesic distance on the sphere, or does it mean the chordal distance in the embedding space?
Good question. It's not the geodesic distance. It's the distance in the embedding. It's just it's the inverse of the Laplacian on the sphere. It turns out to give this.
I see. Okay, thank you.
Yeah. Presumably on a general manifold, it doesn't have this simple form. It's probably a special feature of the sphere. Okay, so there are terms that I didn't mention here. When p is equal to p prime, there's a self-energy term which diverges. So of course, this will be regulated by the UV cutoff of the theory, the fact that the vortices have a finite size. But so there's going to be some contribution from this, and this will give an interesting log-enhanced correction to the dimension of this large charge operator, which looks like this. So it has this log Q enhanced. So there's going to be the usual Q to the 3/2 part, which is still the leading contribution. But before the square root of Q correction that you see in general, there's going to be a log enhanced correction from these fugacities of the vortices. And this term is basically counting the number of vortices. So it's just proportional to kappa and otherwise has this form. So basically what we found is that the ground state has this dimension and has spin 0 as long as kappa is not equal to 1. And for kappa equals to 1, the ground state has a large spin. So the lightest operator at a fixed large charge in a CFT where kappa equals to 1 has a huge spin equal to Q/2, which is pretty surprising. I don't know an example of a CFT that actually has kappa equals to 1. It would be interesting to see if that can happen. Okay, so here we kind of treated the vortices classically, and that leaves a few questions open. The first is that when kappa is not equal to 1, we found that the total classical angular momentum vanishes, but the state still looks inhomogeneous. I have vortices here and there. So we'd like to ask, that kind of seems at tension at the quantum level. Is the spin truly 0 and the state homogeneous, or is it inhomogeneous? So this will be able to answer by quantizing the system. And quantizing the system will also reveal the spectrum of vortex excitations on top of the ground state. So we're going to quantize this vortex superfluid system. To leading order, they're essentially, the two sectors are basically decoupled. And the superfluid sector is essentially unchanged from the parity preserving case. So the quantization follows from what was already done in this paper. So I'm going to focus on quantizing the vortex spectrum. So in the dual language, each vortex is a charged particle in a magnetic field. The magnetic field is given by this in terms of the total charge of the system. And a charge. So we have our sphere, and there's basically a kind of big monopole that's sourcing a magnetic field, magnetic flux through the sphere. And we're putting charged particles. We're putting kappa charged particles on the sphere. That's the picture. So these particles at the quantum level are going to populate Landau levels on the sphere, or also known as monopole harmonics. And monopole harmonics, unlike spherical harmonics, start with a very large degeneracy if you have a large number of flux. Okay, the smallest spin you can have in a monopole harmonic is related to the flux of the monopole and is going to be Q/2. So the lowest Landau level already has a huge degeneracy, but this is what usually happens with Landau levels. The total degeneracy of Landau level is the total flux going through the system. So the higher Landau levels will be at an energy of order B over the ground state. So they're going to be above the EFT cutoff. So only the lowest Landau level is within reach for us. But it has a lot of states. It's extremely degenerate. So a lot of interesting things can happen already in this lowest Landau level. Okay, so when kappa equals to 1, we have a single particle, which is placed in this lowest Landau level. So we simply recover the result that we found classically, which is that the total system has a spin J equals Q/2. Okay, and the particle, so it's going to be very degenerate. When we increase kappa, we'll have more particles, each with spin Q/2. So there's going to be a richer spectrum of states, and there's going to be a number of ways that these harmonics can combine to form states of various spins. So let's start with kappa equals to 2. In this case, we'll have a large number of possibilities for states with spins going from 0 to Q. And if I don't have interactions, these are all degenerates. But the interactions between vortices are going to lift the degeneracies between all of these states. Okay, and so the interactions between vortices come from this log interaction, this Coulomb interaction. And here I removed the self-energy terms, which just gave the contribution that I talked about earlier. And here the J's are the spins. Every vortex, basically every vortex maps to a spin, and they satisfy the usual SU2 algebra. So we basically have a kind of map from our vortex system to a system of all-to-all interacting spins with this simple Hamiltonian. So I'm going to focus on the case kappa equals 2 because in this case you can actually diagonalize the Hamiltonian and find the solution analytically. Because I know that both so when kappa equals to 2, I just have 2 spins. Okay, and each spin, each J has spin Q/2. So I know that their squared, their Casimir just gives me a C number equal to this. And then I can label states by the total spin so that the sum of the spin squared gives me the Casimir of the total spin. And in terms of these 2 C numbers, basically these 2 C numbers diagonalize this Hamiltonian when I just have 2 vortices. And the Hamiltonian takes this form. Yeah, so the Hamiltonian takes this form as a function of the charge Q and the spin J, the total spin J of the state. So here we see that the lightest state is the spin 0 state. And then if we expand around, for small spin much smaller than Q, it will lead to this kind of dispersion relation. Okay, the higher spin states will have a higher energy, but the splitting is very small. Because Q is very large, there's only a very small splitting due to interactions of these higher spin states. So what we learn is that these, because the splitting is so small, we have extremely soft excitations, which are much softer than the phonon excitations. So here I compared the spectrum of vortex excitations, plotting this function compared to the superfluid single phonon spectrum, which basically has a linear dispersion relation. Here it's quadratic, but it's suppressed by a high power of Q. And so if you ask for the lightest operator in these parity-violating CFTs at large charge and finite spin, the answer is going to be the superfluid ground state plus an excitation of the vortices. And this will be so this is the dimension of this vortex system this single vortex that I'm plotting over here. So here this is the answer for kappa equals 2. For larger values of kappa, you can't solve exactly this Hamiltonian. There are too many matrices. But we think that we have an argument in the paper that shows that the spectrum looks basically the same. There's of course more states, but the lowest state again has the smallest spin possible, and then there's this kind of dispersion relation for low-lying states. Let me say one more thing. So here, of course, the vortex spectrum is kind of a small fraction of the whole spectrum, because the superfluid phonon is really a many-body spectrum. Okay, there's many. This is the one phonon states, but there are many phonon states. Whereas in this kappa equals 2 example, this red line is really the whole vortex spectrum. So it's a small part of the spectrum of the whole theory, but it's an important part because it's the lightest. It is the lightest excitation. Okay. So if there aren't any questions about this, now let's revisit this problem of anyons, of the anyon CFT, and place it on the sphere and see see if these things are borne out. So first one comment, when we looked at this anyon CFT on the plane, we found that we could integrate out the fermions and generate an effective field theory for the gauge field. And by this way, we measured C1. Okay, we showed that the CFT becomes a superfluid, and we measured the leading coefficient C1 in this theory. We could have worked harder and gone on and to get subleading terms, higher subleading in derivatives or in higher amount of fields in the effective action for the gauge field, and therefore determine kappa. So in principle, it could have been possible to determine kappa in this way, but it's pretty tedious to do this explicitly, to integrate out these Landau level fermions. And so here I'm going to show you a much simpler way to obtain kappa. Basically, we're going to see that the same effect is happening in this theory, and this is going to give us the value of kappa in this theory. So we're going to place it on the sphere. So again, we need a large charge background. So we're going to have a finite magnetic field on the sphere, so that its integral is equal to the charge. And again, to leading order in K, our fermions will just be free, up to, again, the constraint, of course, that their density is equal to K times this charge density. So if I integrate this constraint equation on the sphere, what one finds is that the total number of fermions is equal to K times the total charge, or the total flux, magnetic flux through the sphere. And this constraint equation, again, came from the A0 equation of motion. So now we're again going to, so these fermions are again going to, the states available to them are going to be these spherical Landau levels or monopole harmonics, except now they're fermions, right? So they're by Pauli exclusion, they're going to have to start populating all of these states. So they're going to start filling up Landau levels. And if we wanted them to fill K Landau levels, so remember that monopole harmonics, their degeneracy is the lowest Landau level already has a large degeneracy, but these monopole harmonics have higher and higher degeneracy as you go up because the spin is increasing. So to fill up the K first spherical Landau levels or monopole harmonics is going to require this amount of states, so K times Q plus K times K plus 1. So if we only have KQ fermions because of the constraint equation, we're not going to be able to populate all the lambda levels on the sphere. The last lambda level will have K times K plus 1 missing fermions. Okay, so we won't have exactly K-filled lambda levels. In other words, in the last lambda level, we're going to see K times K plus 1 holes, which are charged. And these holes are precisely the vortices expected from the effective field theory. Okay, so this tells us what kappa is and kind of identifies what these vortices look like in this specific theory. So this was the C1 we found earlier, and this is the value of kappa. Here, one comment. So I'm assuming that here I assumed that Q was the largest number in the game again, because if K squared, in particular, if K squared becomes larger than Q, these missing fermions will not only deplete the last lambda level, they're also going to entirely deplete it, and they're going to start depleting the next lambda level and so on. The holes are going to leak into the lower lambda levels. So from the EFT perspective, what's happening is that our vortices are starting to talk to the next lambda level. So this is beyond the reach of the effective field theory. But here, from the CFT, we have a microscopic description. We can just see what's happening. We don't need to use the effective field theory. And it's pretty clear what's happening. It's not too drastic. All that's happening is that we're actually completely emptying a lambda level and starting to deplete the lower lambda levels. And so so what one can do, and what we do in the paper, is you can slightly extend the effective field theory to account for this. So what's happening is that if I integrate out the fermions now, since they don't have K-filled lambda levels, but say K-1 filled lambda levels, integrating them out won't quite cancel this Chern-Simons term, but will leave that there's going to be a residual Chern-Simons term in the effective field theory with a coefficient of order 1. So usually you would think that such a thing would gap out the photon, but the reason it doesn't, and it would in general if all coefficients were of order 1, but the reason it doesn't is that the stiffness of the photon is very large. So the coefficient of the Maxwell-like term is k to the 3/2. So this order 1 Chern-Simons term only gives a tiny immeasurable gap to the photon, which actually is not even, you can't even see it on the sphere. So including this kind of extends the effective field theory and explains what happens in this situation. Okay, so I guess there's 5 minutes left, but that's basically what I wanted to say. So thanks a lot for your attention, and I'll take questions if there are any.
Thank you very much. That was a very nice talk and really interesting stuff. So yeah, let's thank Luca for giving this talk. Are there questions for him? You can
Luca, can I ask?
Go ahead, yeah.
Oh, sorry, someone.
Go ahead, go. Oh.
Luca, can I ask? So when Javaris, Muhammadjanov, and Jaboidov did their bootstrap analysis, I can't remember, but did they assume parity as an input?
Yeah, that's a good question.
Because they concluded. Sorry, I didn't mean to.
Yeah.
I thought they concluded based on very mild assumptions that that the gap was order 1. And I mean, this would be a counterexample. So I mean, maybe they just assumed parity, but
yeah, that's a very good question. One should check if they. I know that it's pretty tedious to account for parity in this bootstrap approach, just because there are many new structures that can arise, and which is also why not that many parity violating CFTs have been bootstrapped.
Nice.
But I don't know if they actually assumed it. Yeah, that would be actually interesting to look at.
Okay, no, thank you.
Luca?
Yes.
Can you use this to say anything about the Bostonization dualities in 3D?
Can we say the same thing? Meaning, does this apply to these CFTs?
Can you check the dualities, Bostonization dualities using this? So you did the hard part, right? You did the fermionic side.
Yes.
What happens on the bosonic side?
Yes, I didn't quite do the hard part because the fermionic side is weakly coupled. The bosonic side of this is so it's going to be SUK gauge fields coupled to a boson.
Mhm.
And
I mean, okay, so take K equals 1. You're right. So the weakly coupled description isn't going to help. But let's say you learn new things about this at strong coupling too, right? Using your analysis. So let's say K equals 1.
Yes. Well, what I can't do is prove to you that one of these strongly coupled CFTs does indeed become a superfluid. But if we assume that it does, then indeed then I can make some statements.
I see.
So
Okay.
so when K equals, but actually K equals 1 is special.
Right.
Well, it depends if it's 1 or 0, depending on your, because it has time reversal symmetry.
Yeah, so I mean the one that doesn't, yes.
The one that doesn't. Okay, yeah, then absolutely. This should be a strongly coupled CFT where I expect this to apply, but I don't have a good idea for how to check it. It's also hard to, put on the lattice.
No, okay, but I mean just general argument. So for example, you saw that the dimension goes like KQ to the 3/2, right? K is also strip out 3/2. Can you see this on the scalar side from some general arguments that K appears in the same way?
When both N and K are order 1,
right.
I think not, because I don't think you have another handle than this large charge business.
I see. Okay.
So, but there are, I mean, there are checks when you have some other large number, which I mentioned. But if you don't have any, I think it's hard to give an alternative check.
Okay, thanks.
Are there any other questions, comments, remarks?
I actually have one. So is this thing I was asking you before about the double scaling? Because I was expecting that you would have told me at the end that the conformal dimensions was going like Q over K to the 3/2. And I guess it's true because C1 is like 1 over K K to the 3rd, right?
Yes. Yeah, exactly. Yes, I had maybe I had this a while ago. So in the analysis in the plane, this is really for Q much larger than K, but one can actually show that this leading answer is correct to all orders in the double scaled in the quantity Q over K. So if I scale away, let me just write this as K to the 3/2 times Q over, sorry, K to the 3 times Q over K to the 3/2. This Q over K to the 3, this expression to leading order in K is exact, turns out to be exact to all orders in Q over K. And this is why actually it agrees with these results, which took the opposite limit.
Okay.
But yeah, I expect the general answer not to be as simple. So the subleading corrections should have a non-trivial double scaling limit.
But in general, is there anything known about a finite K? I mean, I was just, it's really the same question that I asked you before. I mean, can you compare with stuff than a finite K? Not just one, I mean.
Yes. Well, I mean, so these, so you mean finite K and large Q, or? For
example, I mean, I was just wondering how much one can compare. I mean, you did the large K, right? And you find that the behavior is what you would expect with 3/2 and so on. So I was just wondering if there were other systems when one could compare with. I mean, if you expect, I guess you would expect this to be true for any K, right?
Potentially, yes. I mean, there's even a question of whether these things are CFTs, exist as CFTs for any K.
Okay.
And I mean, we think so, but there's, there isn't a proof for sure. So yeah, I would expect it to hold. I mean, and maybe, okay, so I made a little comment on this, these large N versions of this. So that's an example where it's not a superfluid, okay? And I expect this stuff not to apply. But and in fact, it was shown that it was a Fermi liquid. But here, I think maybe you could do a check that's different than the one we did. So this would be a new class of theories where you look for 1 over n corrections to this to these CFTs, and in particular to their finite density states. And our expectation is that there's going for any finite but large n, there's going to be kind of relevant effects in this Fermi liquid, which will lead to a breakdown of the states. There's going to be a scale of order mu over n, or some power of n, above which you still have your Fermi liquid. So it's a very small energy scale. But below this scale, there's a breakdown due to IR effects, that leads to, maybe a superfluid or maybe some some other state of matter. So I think that would be an interesting place to look at, where you do have perturbative handle, and it's a bit more complicated and interesting than the CFT